Today I am going to present about classical simulation of quantum circuits, especially about extended stabilizer simulation. So let me start to introduce myself. I'm sophomore year in electrical and computer engineering department in Seoul National University, and I'm in SQRT since 2023. I am an undergraduate intern in QISCA, Quantum Information and Quantum Computing Lab since July 2024, and I'm researching into classical quantum circuit simulations. So this is my introduction about this presentation. So first of all, we are talking about quantum computing, which involves quantum computers. But now I am doing it with my classical computer. So why do we need to simulate quantum circuits? And we know that we all have belief that quantum computers cannot be efficiently simulated by classical computers. So one of the researchers that research about this particular topic, David Gossett, said to quantify what is hard to simulate classically and to verify and validate small quantum computers like near days, like we have ion trap or like superconductor, they are a little bit small to use now. So that is more to like validate by classical simulators. And to believe that we cannot simulate quantum circuits efficiently with classical computers, so we can strongly believe that belief above. So the problem with the classical simulation is about the size. To control the n qubit vector, it makes 2 to the power of n, right? To consider 0 all the way to 0 and 1 to 1. So we need to simulate that by state vector simulation, which involves 2 to the power of n times 2 to the power of n matrices and 2 to the n size vectors. So this consumes time and memory. And maybe someone can reduce one of them, like using the all bases inside between the gates. That makes like less memory, but that makes more time. So maybe either one can be reduced, but not both. So what I'm going to present with is the red one, and there are many approaches to this problem. Like we need to approximate the result because we cannot make it in time or space. So some approaches like matrix product states, that is most popular one, and this is from 2005. And if you are interested in here, then we can check it in that archive. That uses tensor product, which is I think popular in physics, the principle about that, but I don't know because I'm just electrical and computer engineering major. So, and that one, and the second one is a little bit unpopular, but that makes a sense, so I just included it. And third one is what I am going to present, which is extended stabilizer simulation. So to talk about this, I need to talk about what is stabilizer first, and then I need to talk about the simulation of quantum circuits in general. So the first one that is above that is the one that I need to use for introduction of stabilizer, and the second one will be the main one. So this is the overview. So I'm going to talk about the extended stabilizer simulation, which has simulations of Clifford gates and then extending that to non-Clifford gates. So first of all, we need to talk about the stabilizer simulation. Stabilizer simulation involves stabilizer, of course, and stabilizer is a gate that is specific to a state that satisfies U psi equals psi. So considering global space phase, like Z0 would be 0 and minus Z1 would be 1, like that. And the set of stabilizers would be the sets of stabilizers about that phase. And for specific purpose, we restricted to the n poly gates here, then the Clifford gates is related to this S psi. So S psi and psi is 1-to-1 if that has made from Clifford gates. And because of that, the Pn, which is a set of n polygates, has 4 to the n dimension. Half of them would be a stabilizer of them, and half of them would be not. So that makes the n stabilizer states generate S psi because it makes 2 to the n, right? And for initial condition, like all 0 would have Z1 to Zn as the stabilizer. Here we need to use that they are pairwise commutable because that makes they are the independent set of generators. So the gate application here, like to G psi, we can just use the conjugation here, GU dagger. This makes psi to G psi. So that makes GU dagger as the stabilizer of G psi. So S psi is a subset of polygates, so they are tensor products of X, Y, and Z gates. And if it is 2D blow circle, then it will be just Y is about the same to XZ. So here the stabilizer simulation, the original one, is just a shot generator, so it just didn't care about other global phases that affects like I or minus I. So that makes just compact storage of information of that phase as X and Z. Just that for N stabilizers, they have all N qubit X or Z gates, and that's the tensor products. So whether it is R in X, R in ith qubit or not would be just the storage one. So total n of 2n plus 1, which includes minus n plus for the global phase one. So that adds plus 1, and that makes just a 2 to the 2n squared for storage. So it would be an efficient one for stabilizer simulation, which restricts in the Clifford gates. So to use this storage and update it, we need to prepare our all G dagger PG for all possible P. So if we want to get use a gate, apply a gate, then we need to update by that GUG dagger here. So we need to have all X and Z component, how they change. And if we have their like formula for that, then we can just apply the formula, which is just takes ON to ON squared. So that makes just a simple simulation of Clifford gates by ON squared or ON cubed. Because this is just a stabilizer's introduction, so I'll just skip the practical implementations. And if you have like interest in here, like I have uploaded the paper with this, so you can check it there. So we have this shot generator, and we need to extend this to a non-Clifford gates. So this is what extended stabilizer simulations extended means. So we know that Clifford gates is simulable by polytime, but if it is non-Clifford, then we can take that as a sum of Clifford gates. So we can say that stabilizer states are just a state that can be generated by Clifford gates. Then we can say that those phi i's are classically simulable by polynomial time. And if we can represent non-Clifford, like non-stabilizer state psi into some sum of stabilizer states, like weighted sum, then maybe we can just take it that as a polytime simulation times that number of stabilizer states. So for example, T is not a Clifford gate, but we can say that plus is 0 plus e to the I pi over 4, 1, which makes two stabilizer states just added by themselves. But I missed the square root of 2 here. So there are two different ways to implement this, to extend the Clifford gates. And first one is just to add the gates to make one non-Clifford gate. So if I have Ki, which is a Clifford gates, then we can just make a V equals Ci Ki, which needs to be found. Like generally, we cannot find Ki with just a given V, but if we have a method to at least represent like T squared or like T to 6 qubits or something, then we can just approximate them as in order to fast simulate here. And we can just copy the previous results. Like if we have one stabilizer state and we need to apply a non-Clifford gate here, then we can just copy and paste all the present states, and then we can just apply it one by one, and then we can add up all of them with we know with the coefficients we know. So if we have like V is non-Clifford here and U is Clifford, we can just make that long gates into a sum of products of Clifford gates. So this is one, and the second one is the gadgetization. This method is more old here, and the paper I brought here is about the first one, which is the recent one, and I think, but this is more like more straightforward here. This uses the state injection, which takes psi as an input, and if we have the magic state, which is just a non-Clifford gate applied to plus qubits, then we can just make that as C naught and measuring it, and then post processing it makes the V to apply to the states. So if we have V plus as Ci phi I, which has the phi I is a stabilizer state, then we can just make it that as one of the initial qubits under there. So we have our qubit to simulate upward one, and we have other non-stabilizer states represented by some of stabilizer states as the qubits for the ancilla represented by V here. And if we use this, then we can just prepare if we use like 3 T gates or 6 T gates, then we can just make T plus with six powered T plus here. Then if we can prepare that easier, like if we have T plus 1 by 1, then it needs 2 and 2, so it's 2 to the power 6, which makes 64. But if we just have T6 plus 6, then if we can represent that as a sum of 6 stabilizer states, then we can say that 6 T gates are just a copy of 6 stabilizer states. And actually that is possible here. So we have 2 different simulations here, and we need to talk about how this works and how much this takes. So if we represent V plus as K different elements, like the stabilizer states, then we need to copy K states, right? To apply one by one different one. Then we need to make that copied one by one when we need to apply a gate. That makes exponential to K, the number of stabilizer states that has to be represented for V. So for this K is called the stabilizer rank of V. So for example, as I said, T, the stabilizer rank of T would be 2, and T squared would be also 2. So we are just finding that, but there's no like general formula for this. So we can just make like trial and errors to find more efficient one to simulate. And the best one here would be the T6 here, and that makes 6 stabilizer states. So for gadgetization, if M T gates are prepared and we can make it like in group of T gates, then we can divide by M, divide the exponent by M, so this makes exponential speed up here. And so for this one, yeah. Yeah, we can improve those because we need to simulate here. So we actually found the combinations for that. Yeah, so if we use T gates only here, then we can use that T6 for like if we have like 31 states, 31 T gates, then we can group up by 6 and then use 1 for the chi T equals 2. So we have a total of 6 times 6 times 6 times 6 times 6 times 2 stabilizer states to start for the gasitization. And for sum of Clifford, this doesn't use the K here, but it just use the probabilistic sampling here. So it just shots the stabilizer state here to just according to the CI here. Like if we have T plus, which is 0 plus e to the I pi over 4, 1, then actually both of them are just a probability amplitude of 1 over 2, right? So we can just sample through that to make one sample of stabilizer state that can represent one sample of the psi. So if we just repeat making Ci phi I here, then we can maybe estimate psi here. And this paper says that this is quite good to estimate here, and I think it makes sense here. So there are two different ones. Like there are Markov chain simulation, which just takes px, which has a little bit of problem here because when we apply the gates by CIKI, this makes the gates sum, which doesn't ensure that this CIKI makes a normalized vector, because if we just take it as shot generator, it doesn't match with actual amplitude and the probability here because it loses the phase and all the sort of things. So for that, we need to one approximate the denominator, the length of psi when we shot the result, or we can just take satisfy with px but without normalization, because we can calculate the phi to inner product of x and phi, which x is a bit string here. Then we can just take that as a reference to Markov chain simulation, because that just takes the ratio of probability to produce the sample here. So at least this is a shot generator, so it takes the possibility of px here, but this px can be calculated for all the 2 to the n possibilities, but that is too much, so it takes too much time. So it just Markov chain simulates here to generate samples of x here. And the approximation of psi square here would be calculating all x, all possible x to calculate all px to perfectly generate the shot generator. Yes. Um, they are as this is a probabilistic simulation, there are error tolerance parameters, and delta is the um, delta is the tolerance for not being right, like the difference between the real truth and ground truth and the sample value. And for that bound, that error bound, the simulation would simulate that uh, successfully in that error bound by a probability of 1 minus epsilon. Right. But for that, the simulation here does not ensure normalized values. So, um, sorry. Right. Oh, that is the total result. So, so like we can simulate the x here, right? So we have the probability density function for the ground truth function for px here. And yes, uh, uh, as I remember, it is about the maximum value for like there are just 2 to the n bit possible bit strings. So the max one, the maximum one, and divided by 2, I think it takes like norm and subscript TV, but I don't remember that much, so I'm not sure. Yeah, but you can check it on my drive, the paper in my drive. And the gadgetization, and this has also 2 different ways to simulate here. And when we state inject, we need to adjust, like the post-processing would be needed. The C1 to CT would be the one. And if we can simulate through the gates that we can ensure that there are just 0 for all of the measurements, then we can just um, ignore the C1 to CT, because the chance of coming out 0 to 0 coming out must be non-zero, because if some bit must be 0 or 1, then we can just make it that as just a Clifford gate without the making it as a 1 non-Clifford gate. So if we have non-Clifford gate, then it must have um, chance for 0 to 0 for V plus. So if we can find that, then we just don't have to consider C1 to CT. So we can just ignore that. And if we just C naught and measure, and we just think that that has all measured by 0, and we just update the stabilizer simulator for that measuring results, then we can just make it as just V psi for here. But this uh needs the V plus to be perfectly calculated, because if we don't, then maybe that would not have all 0 values, because if we approximated it, so the approximation error would be multiplied every time if I make the measurement results just assumed 0. So to fix that, we can use just random sampling here. So we just sample according to the gates and the phase status to choose 0 or 1 through for the ancilla qubits. then we can just Clifford simulate for each of the results according to the results, and we can just simply propagate through them. But this makes the non-Clifford gates to have one condition, because the C1 to CT, they have to be Clifford. So for V, they have to be like third Clifford state, which makes G dagger makes Clifford here for polygate U. Is it okay? I think it is not straightforward enough to just understand it in one glance. So if you have any questions about this, like, feel free to ask it to me after this presentation or something. So we now found that sum over Clifford's method does not ensure normalization and gadgetization. They have to process. So for that, to deal with that, they have two different ways to simulate for each one, and these would be the extended stabilizer simulation. But one question remains. We have Clifford simulator, like the stabilizer simulator, as a SHAT generator, because that is the problem, because that doesn't include phase. We need to simulate the stabilizer states as they are. They need to be phase sensitive. So original Gottesman and Nil, or Aronson and Gottesman algorithms, does not consider phase. So we need to add them with the global phase here. It must be the global phase, but we need to add it, so it does not make that a global now. So we need to make a Clifford simulation with phase. And the key idea is every stabilizer states, or the state that can be generated by Clifford gates, can be represented as phi equals omega UC, UH, and S, where omega stands for a global phase, UC is a C-type gate, H is a H-type gate, and S is a binary string, so 0 to 0 or 1 to 1. And initial states would just have omega equals 1, UC1, UCI, UHI, and S equals 0. And the C-type gate and H-type gates will be explained in the next slide. Yeah. So the C-type gate and H-type gate are the gates that satisfies UC 0 equals 0. So UC is a stabilizer of a state 0, and UH is just a tensor product of a Hadamard gate or Hadamard gates. For UC, S and C naught and Z are just on the UC, and UH just contains the H gate. So all of the Clifford gates except H would be included in UC. So for UC, you see, like, the previous one considers about G dagger PG to update according to that gate to encode the states into X and Z components. And for this also takes that approach to prepare about UC dagger PUC, and all of them has things about XP or ZP here. So if I apply X on the P qubit, then it will respond as those I to the gamma P and product of X and Z according to its each P qubit here. But we can insist that UC dagger ZPUC does not contain X, because that's why we call that as a C-type gate. Because if it has UC, then it cannot have any difference if I apply Z here. So it does not have any change of 0 to 1 component. So we can just easily prove that with the first equation, applying Z and then UC dagger. So for the response of applying X gate in P qubit and Z gate in P qubit, that makes a response of all of the possible X gate or Z gates into other qubits. So we can store that information to F, M, and G with the phase vector gamma. Then we can just take UC, which would be the 2 to the n times 2 to the n matrix, into n squared matrix, n times n matrix, 3 of them, and then one n vector. So that makes a storage very easy with these. So this FGM gamma would have about UC, and UH is just B because it's just a tensor product of H gate, which has just we can just store the information by whether the qubit in P has H or not. So we can just have a binary vector for V, and we have S and omega for the bit string for the base case and omega for the global phase. So we can just have total of 7 values, F, G, M, gamma, V, S, omega for one stabilizer states that has to be represented by omega UC UHS here. So we can now compose phase sensitive stabilizer states as ON squared here. ON squared storage, and of course its updates would be ON squared, and the measuring would be ON cubed here. So we need to find FG, M, gamma, V, S, omega here to update the stabilizer state. So we can inductively approach to that state. So building Clifford gates up one by one. So if we start with 0, then if we have one C-type gate applied, then we can update UC to gamma UC. And of course, there is no UC realized in that simulation because they are just virtually spaced in F, G, M, gamma. So we can just change F, G, M, and gamma according to that C-type gate gamma. And H-type gate also, we need to apply that to the left of the UC, but we need to store that H to the second one, right? Because UC is first and then UH, but H gate is now after UC, before UC. So after and before would be actually mean the same thing because the matrix multiplication order is reversed. But so we need to update UC and UH when we need to apply H gates. So we now using the equality HP equals 1 over square root of 2 XP plus ZP. So we just apply XP and ZP, both of them separately, and we can add them. And for XP UC UH and ZP UC UH, it can be not that intuitive, but we actually already prepared for that because the definition of FMG and gamma are already using XPUC here. So actually this is a more like a commutator here because if we have XPUC, then we can change it to UC and what? So the question mark here, so like we have polygates applied to UC, but we need to have UC at the front. So we can we need to change the order, and that order change is already constructed by UC dagger PUC. So we can apply XP to UC UH to use that definition of UC, and we can just one by one. Sorry for adding UC here on the first equation of XP and after the first equal sign. So we just make XP as sorry, it wasn't wrong. So we can apply XP before UC to change the order as intended because we already know how to change the order by UC diagonal PUC, and then we can just change the order and then change the order to have UC UH and then have XZZX components there, and they are going to be just applied to the bit string S. And then ZP is also more easier because UC is just a gate with C-type gate, and Z is also a C-type gate, so we can just move that out. So we have same UC UH here with different afterwards, and adding those up gives these different values. And omega UC UH is also already here, and we just moved all of the X and Z gates to the most right. And if we apply that as to the bit string S, then we can have different set of S and omega for both case X and Z. I think this part cannot be explained in 1 hour, so let me just skip here, and you can follow through this presentations to understand, but I think I recommend to read the paper for this one. But I think similar time will take for this one and the paper, because the paper is not the original one to introduce this one, so it also have like more broad explanation here. So, and so we can end the H-gate application by that omega x sx plus omega zs z to some bit string here, and that bit string generation requires S and H to be applied after UH or before VC here. So VC, S, and H here are the like leftovers to match the C here from SX and SC, and they are just implemented by the stabilizer simulation as just they update in original stabilizer simulation, and UC would have like right and left multiplication of C-type Clifford gates. And that concludes how the extended stabilizer simulation works, including the sum of our Cliffords and gadgetization parts, and the base of them as the phase-sensitive simulations for Clifford gates. I think this is the last part of this presentation, and this is how we can make a product of X and phi here, because I already said that we can calculate them as that one, right? Px, the value of Px without normalization can be calculated here, but I didn't talk about this, and this is how it does. And it is actually just easy if we consider that phi is just a bunch of complex number and some gates, UC and UH and S, then we can just substitute that as just UC and UH. Then if we have like bit string X applied here, then we can just make that as 0 and then X gates according to that bit string. So we can just make it as 0n and then the bunch of X gates after, like before that UC and UH here. So we can just do the X gate application, which we already did for the H gate. We can just do that here and then make all of them as a gate of X, Z, and H between 0 and S. So for that one, so we have, it's actually just Clifford simulation. So it has just one of the 6 states in Blow sphere, and for 6 to the n possible phases. So like 0, 1, and minus, plus, and plus I and minus I. So just we can just take that as a reference to have confidence about the values here, because it would be just a 2 to the power of n or something different for like it would be at least power of the square root of 2, because they have just X and Z and H, so it would just have, it would be 0 or 1/2 to the power of something, which is just all of the same because they have just equal probability, because H does that and does that only. So if we just calculate here, like the 0 to the n and xj, zj, and h, if we have something that makes 1 from x, z, z, xj, zj, h, and s, then it will be multiplied with 0 at the left one. Then it just makes the total inner product 0. And if not, then it must be checked through all of the qubits. That has to be makes all of them 0. Then, or at least they have h, because h makes like it can be either 0 or 1, which does not consider x or z or something, because it would just multiply with 0, which makes square root of 2 over 1, 1 over square root of 2, or not. So if it has h, but then it would be just a 1 over square root of 2. If not, then that makes vulnerable to be 0. And if to prevent it, it has to be x and s is 0, or no x and s is 1. So both of the conditions will make the value 0. And if not, it will be just uniform through the possible outcome. So it will just make the inner product of 0 or 1 over square root of 2 powered by some value that makes the value, like the number of h gates there. So I think, sorry for my like stuttering, because this is my not my first language. So, but at least I tried my best, and thank you for listening, and I will wait for all of the questions here. Thank you.